out of our, oops, I keep receiving messages from Zoom. We are just out of our spring IJMF seminar series, which was extremely successful, and we have been, Bal and I and the organizing committee, extremely pleased. And we are now ready to start with even more enthusiasm a new autumn series. The autumn series will have 6 seminars. The first one is, of course, given by our friend and colleague Greta Tryggvason, is the speaker of today. And I will just leave to Bala the word to make a proper introduction of Greta. And in the meantime, I have to welcome and thank you again for joining us from many continents and especially many different time zones. So thanks a lot. Bala, the word is to you.
Good morning from my end. Good afternoon, good night, all over the world. First of all, Alfredo, can you hear me?
Yes.
Very good. It's a real pleasure. I want to join Alfredo in welcoming all. Given the challenging circumstances that we have had for the past year, this is wonderful that we could meet every so often, our friends, virtually and talk, and also get the pleasure of listening to one of our distinguished colleagues give a talk on a topic of their expertise. Today we have Greta Tryggvason. Certainly to this crowd, he doesn't need any introduction. We all know him, both him and his work even more. But let me give a short introduction. He is currently the Charles A. Miller Junior Distinguished Professor at the Johns Hopkins University. He is also the head of the Mechanical Engineering Department. He received his PhD in 1985 from Brown University. I had just joined there as a younger graduate student at the time, so he was one of the role models there, and he still remains as one of the role models. After a PhD, he worked at, did a postdoc at Quran, then went to University of Michigan, where he was a faculty. Then in 2000, he moved to Worcester Polytechnic, where he was the head of the department. Then he moved for 17 years. He was at Notre Dame. He was the Viola Hank professor, and he built that aerospace and mechanical engineering department. He's very well known for his work on computational fluid dynamics. Particularly, he's the pioneer in the direct numerical simulations of bubbly flows, interface resolved flows. His codes and his students have spread across the world, contributing and continuing the trend that he has set. He was also the editor-in-chief of Journal of Computational Physics, which is absolutely the best in the business. He did that for about 15 years. He's decorated, well decorated. He's a fellow of APS, ASME, AAAS, and a recipient of many awards, including ASME Fluids Engineering Award, and last 2 years back, ASTFE Fluid Mechanics Award. So Greta, I have chewed up a couple of minutes of your time. Without further ado, I want to turn the podium over to Greta, and we're looking forward to your talk, Greta.
Thank you so much. Let me share the screen here. Let me put it in presentation mode. So you see the presentation mode, the slides and everything?
Yes, Greta, I can see it very well.
Very well.
Okay, very good. Okay, well, first of all, Paula, thank you so much for the introduction. And also thank you so much for the committee to invite me to give the first lecture. I did watch, I think, all the talks last year, and I was very impressed. So it's a great honor to be invited to start this off. So I'm going to start this by just a few videos here of bubbly flows and dispersed flows. And the point of these movies here is that we actually can do these relatively routinely now. Indeed, the movie on the left is, I think, more than 10 years old, which is bubbles, highly deformable bubbles in a turbulence channel. So I want to start with this, and I also want to start by making sort of the main point of the talk, okay? And that's basically that we have really come a long way in doing direct numerical simulations of multiphase flows. Indeed, we have come so far that many of the initial challenges are behind us, and it's time to move on, okay? Every time we make progress, we open up new avenues. And I'm going to talk mostly about two directions. There are many directions, but I'm going to talk about two directions and show you some examples. So first of all, I think we're now ready, and actually people are trying to go to much more complicated problems. Now, when I say more complicated problem, I don't mean problems where you sort of add one physical process, such as in heat transfer, boiling, mass transfer, and so on. I mean processes where there are lots of multitude of physics sort of taking place, and you really need truly to do a multiscale approaches. The other topic is, of course, that in the past, you know, when we were doing this, the goal was a paper and maybe a movie, but we really have data now that we should be using to improve our capability to make predictions in a transformative way. So I'm going to give you examples of our recent work on both topics, but I think if you look around, we're going to see that there's a lot of things happening in this field, many that align very well with those 2 points that I made. So I put DNS in the title because we have been talking about DNS for a long time, but I thought I would sort of clarify, what do I mean really by a DNS? Okay, what's happening here? Yeah, here we go. Okay, so what I mean by direct numerical simulation is sort of based on what it was originally called for turbulent flow. Now, you can call DNS anything DNS, but when I say DNS, I mean something rather specific. There are really three definitions. First of all, the solution is independent of all numerical parameters, method, and so on. So in effect, the solution should be an exact solution of the equations, okay? And this is usually assessed by verifying the solution. Secondly, we assume that the equations describe the physical process in a reasonably accurate way. This is what is called validations. But also, we are really not just looking at fully resolved solution of a simple system. We're really looking at systems that have a multitude of temporal and spatial scales that all interact. And we are interested sort of in the statistical properties of the system. Now, the reason that I bring that up at the beginning of the talk is because as we move to more complicated systems, the rather high bar established by this definition is becoming more and more difficult to satisfy. When we have very complicated systems, like systems undergoing topology changes, as I'll talk a little bit about later, you know, maintaining sufficient or full resolution for all parts of the flow can be very challenging. And as we move to problems with more physical solutions, having governing equations that we are absolutely certain that describe with high accuracy the physics is also becoming more challenging. So in that sense, maybe DNS sort of have run their course because we can now do DNS on many problems, and the problems we are interested in, we really are we are almost doing just almost DNS rather than sort of full DNS according to these situations. Okay, but we also have a lot more experience in doing these kinds of simulations, and we are in better position to assess when it is sort of okay and acceptable to be not maybe fully resolved. Okay. Okay, now just another slide of examples. As I said, people have done this now for over 20 years. This has been applied to a large number of systems, boilings, non-Newtonian flows, phase changes, and so on. So there's a lot of applications. There's a lot that we have done, and there's a lot of problems that where we have really made significant progress using DNS. Now, I'm not going to talk about the numerical approach in any detail. I'm just going to remind you that most progress has been made using what is usually called the one field formulation where we write one set of equations for the whole flow field, and then we have vector marker or an index function that identifies the different fluid regions. It's actually interesting that this is really it belongs to the very beginning of computational fluid mechanics, because this is both the approach and the problems that the people at Los Alamos, led by Frank Harlow, were doing sort of in the very late 50s and very early 60s. Okay, so this is a approach that has stood the test of time. We've tried many other things, but most simulations that are done now are based on these approaches. Now, to solve this equation, we have several methods, but basically most are based on using a single stationary grid and something like a finite volume method to solve the Navier-Stokes equations. You can use other methods. The basic idea is that solvers that have been developed for single phase flow can, with a little bit of addition, be extended to solve these problems, except that we need to track the interface. And again, by now, there are many, many ways to track the interface, many which are highly accurate. We do a particular approach, which is usually called front tracking, but I'm not really going to spend time on that. This has been the topic of many, many articles and even books, and I shamelessly advertise mine there in the lower right corner. But as I say, you can find information on very, very accurate methods. You can find open source course codes and so on, widely in many, many venues. Okay, so just to remind you, I'm only going to show you one slide on bubbly flows. And that's just this exceedingly crowded slide, which has a long list of papers where we study bubbly flows. If you can't fall asleep, this one way is to pick up one of those. The important thing here is, again, that the movie on the right-hand side was made about 20 years ago. So as I say, this is a capability that's been around for a long time. And even on the left-hand side, there is a snapshot from a simulations of bubbly flows in a turbulent channel with a shear Reynolds number about 500 and about 500 bubbles and so on. So as I say, all of those can now be done, perhaps not on your laptop, although I'm certain that the simulation on the right now would run on my laptop, but we can do it relatively routinely. So I'm going to talk a little bit about more complex problems. This is work in progress again, so we have many things yet to do. But if you look at bubbly flows, you will often find that it involves many more complications than just two phases. And the examples here is one that I've shown frequently. It's a production of liquid phase methanol. And the important thing here is that it actually is a three-phase flow because it has catalytic particles that stimulate the conversion of the syngas to methane. And on the lower left-hand side, it's a top of a froth flotation cell. I'm going to talk a little bit more about that, and to know what I was talking about or increase the probability that I know what I'm talking about, I actually visited a small copper mine in Chile and had sort of a first-hand look at what this looks like. So this is not boiling, although it looks like that. This is bubbles being sent up through a slurry containing particles, and it's separating out copper particles and carrying them to the top. Now, bubbles are used in three-phase flows in a multitude of situations, and I picked out two. This is a topic that is currently being worked on by Lei Zhang, who has just recently started his PhD thesis. He worked a little bit with me as a master's student, and this summer joined us as a PhD student. But one application of three-phase flow is in separation. If you have, say, oil and oil drops in water, then if you just want the oil drops to sort of rise to the top, that takes an awfully long time because the density difference is so small. But one way to increase the separation rate is to pump in air. And if the droplets coalesce with a bubble, and when they do, they usually coat the bubble, then of course the oil is much more buoyant, or the oil air mixture is much more buoyant, and the separation is increased. The other problem, actually the one I'm going to talk more about, is froth flotation, where you have two particles, or two types of particles, sometimes more, and some are either hydrophobic and others are hydrophilic, or you mix in a variety of chemicals to make them that, then you can use bubbles to selectively carry the hydrophobic particles, the particles that don't like the water and therefore rush to join with a bubble that passes by, to carry them to the top. And that was the process that I showed you from the copper mine in the other slide. So this is a very complicated process. Okay, and here was sort of a sketch that was supposed to show some of the processes involved. There are bubbles, they're going up to a slurry that is mixed with chemicals. You have thin films that rupture, you have moving contact line, your surfactant cover bubbles, and various variety of things like that. So it's a fairly complex problem. We have done some preliminary simulations. There's a single bubble there that carries, these are actually drops rather than particles. But basically what happens, if I maybe run this again here, is that as the bubbles move through the field, the drops stick to it, and the process by which they stick to it is very, very simple in this particular case. And then they slide to the back of the bubble and is carried to the top. Now, to start studying this sort of in a more serious way, Ley has started by investigating three-phase problems that involve in this case, he actually started with heavy drops rather than bubbles, although he's doing solids now. And we looked at sort of the distribution of drops around bubbles, how they move relative to the bubbles, what the effect of the slip velocity is, and so on. We also did some detailed studies of comparing freely evolving bubbles with sort of a single cell setup, where we just had one bubble and several drops. One of the findings in the paper, which has just appeared in Fluids, is actually that the single cell model is not a very good one, because the differences between that, the droplet distribution and so on, and where we had freely evolving bubbles were actually rather significant. But the kinds of data we developed, and as I say, this is Ley's first paper, so this is sort of the warm-up step in his studies. For some of the results here was that the results of the bubble deformability, which is given by the Eccles number there, actually was relatively small, except that the velocity fluctuations were larger. So here are the delta, the slip velocity for the bubbles at the top, for the drop at the bottom, versus the deformability of the bubbles. And as you can see, that really had little difference. And on the right-hand side, we plotted basically the distribution of drops around bubbles averaged over the bubble. So this is sort of somewhat similar to the pair distribution probability as we do in two-phase flow, except that this is the drop location with respect to the bubbles. And as you can see, there is actually rather little differences between the nearly spherical bubbles that are in blue and the much more deformable one in red, okay? So we are in the process of doing much more with this problem. We are in particular working on trying to incorporate a much more accurate mechanism that captures the sticking. The goal here is to be basically able to simulate bubbles that rise to a surface and capture particles. As you can see, even if you have hydrophilic particles, as you have on the left-hand side, sometimes you get particles stuck in the foam and carried to the top. And of course, if you have hydrophobic particles, not all of them get captured by the bubbles and carried to the top. The frame here on the right-hand side is actually the sort of the first attempt to do bubbles and solid particles with an interface. And as you can see, we successfully have carried them to the top. We haven't captured the drops because there's no sticking in this particular case, but that's where we hope to go. Okay, so this is an example of sort of what I think is more complicated problem, because you have to capture thin films, often affected by surfactants. They rupture. You have triple line contact lines. So it is a very complex problem. Oh, and you have in the foam, you have draining of thin films. So it is a pretty complicated problem. Very little has been done on it to try to simulate it sort of in the detail I was showing you. But it is a very, very industrially and technologically important problem. Of course, it is important for mineral processing because you use it to separate the ore, the metals that you want from the solid. You grind everything into small particles until you're mostly, say, copper in one and rock in the other. And then you use the bubbles to separate it. As mineral deposits, sort of high quality mineral deposits are mined, increasingly the miners are having to go to more less sort of rich deposits. And in that case, the importance of accurately and effectively separating the material becomes important. And this process also finds uses in other areas, such as more recently in recycling of plastics, where you do the same thing, you grind the plastic down and you use flotation to select the right plastic. Okay, so this is one complex problem. Let me talk a little bit about another complex problem that is bringing some very, well, both similar and different challenges. Okay, so, and that is the description of the statistical properties of the flow. So for bubbles, drops, and solid particles, we have decades, if not centuries, of describing the distribution of statistical distribution of drops accurately. We do paired distributions, we do correlations functions. Now, maybe there are some challenges in describing large clusters, but certainly in mixtures that do not have clusters, we have a pretty rich toolbox of statistical tools to diagnose the evolution. In flows that have very complex and evolving interfaces, often undergoing topology changes, this becomes much more complicated. And indeed, it's instructive to look in the literature and see that there are a number of areas where this is actually important. Rheology and combustion are sort of fluids area, but some of the ideas related to characterizing non-homogeneous structures, you will also find discussions in astronomy and so on, where people are trying to look at the sky and identify where there are galaxies and so on. We have looked a little bit at this, and I'm not going to talk much about topology changes and the characterization. This was described in these two papers here. But what we did is we started with bubbles and we allowed them to freely coalesce. Well, not totally freely, we had some criteria. And then we looked at the statistics, okay? And as I say, we tried out many of the standard things. We did quantify the blobs and so on. We did correlations function and a variety of things. You get pretty complex structures. So here is, for example, we identified connected blobs, and this blob there is connected, but it's pretty wild. And then we looked at things like equivalent diameters and sphericity and so on. And one of the interesting things was that as you increase the volume fraction, the sphericity sort of, or the non-sphericity really increased very dramatically, but actually the size of the blobs was pretty close was pretty independent of the volume fraction. So if you look at here, the equivalent diameter, basically assuming this is a sphere, actually remained pretty constant, even though the sphericity varied widely, and there was some distributions here. And of course, in addition to doing this, we did a whole bunch of correlation factors. You can correlate both the velocity field, you can correlate the distribution, and once you have correlations functions, you can do integral scales and things like that, okay? So this is an active research area. Of course, people have done flows that change topology for several years now. Simulating atomization is a big business, and we've been collaborating a little bit with Stefan Zaleski and now Stanley Ling in trying to look at atomization. Most of those are done with a volume of fluid method. We actually have a code that is sort of unified front writing versus volume of fluid called Paris Simulator. And this is done with Paris Simulator. But here on the other side, we have done topology changes with front tracking, which allows us to explore in detail what is the effect of the the topology change process on the statistical properties of the flow, because we can control completely when things coalesce and when they don't, unlike in the when you track the interface by a volume of fluid or level set and so on. Okay, so it allows us a much finer control of that. Okay, so let's see. So I have many things that I want to talk with you about, so I'm going to move reasonably quickly. I also promised Bala that I would done in about 45 minutes, so bear with me if I don't go in too much detail here, but I have a few other things that excite me that I want to talk about. So in particular, this was sort of my first bullet, but I do want to talk a little bit about the modeling. So as I said in the beginning, there are at least two immediate challenges. One is these much more complex multi-scale systems. The other is, what do we do with the data and how do we model it? Okay, and I'm going to talk about three ideas here. One is somewhat sort of old by now, namely using just machine learning for the closure terms. But then there are two other items that I think are going to play a much more important role as we move forward. So this slide is just a review of a work that has been described some years ago in two papers. These were some of the early papers, not the first one, but some of the early papers of applying machine learning to closures in multiphase flow. So we got away with fairly simple things. We just asked what is the average evolution of flow in a channel. You can develop a set of average equation, and we picked the absolutely simplest one, namely an equation for the horizontal flux of bubbles and the average vertical momentum. As I say, you can develop more complicated sets if you want to. We also ignored the properties in the bubble, and that allowed us to average over the whole phase, and that leaves out the forces that you usually see in a two-fluid model. Okay. So in this particular case, the unknown are the flux of bubbles and the Reynolds stresses or the streaming stresses. If the bubbles are not spherical, the surface tension term also appears here. And then the challenge is to find basically the closure, how the bubble fluxes depend on the resolved quantities, such as void fraction and the gradient of void fraction, gradient of velocity, and how the streaming stresses do that. You feed it into a relatively standard machine learning model, and you get a set of equations that you can then solve. So this was a particular case. We did a few of those. It's a case where we had bubbles in a vertical channel. If you release the bubbles uniformly distributed in a parabolic flow, they all go to the walls first, and then some of them come back as the flow slows down. Now here, really should have a better picture for this, but the red line is what the model gave us, basically using the machine learning. And here's the velocity, here's the void fraction. Now the model does not pick up the individual bubbles, so you don't see those, but the rest is actually pretty clear. Now we have also pretty well captured. We have also captured quantities like the flow rate and the wall shear and things like that. We've also applied some of the closures that we learned for one case to other cases, including even a downflow. Okay, now this was done by a graduate student, Ming Ma, who graduated several years ago when he had a few months before he graduated. So one of the things he was looking at was to use machine learning to help us select the variables that govern the flow. For the first problem, where the flow was mostly laminar, this wasn't terribly hard. We just picked those that seemed reasonable. But for more complex turbulent flows, you often have sort of auxiliary variables like dissipation and turbulent kinetic energy in single phase flows. And the question is, how do the closure terms depend on those variables, and which one do we need to model? So this didn't go quite as far as I hoped, but what he did is that we guessed all kinds of variables. He correlated the fluxes and got a pretty good correlation. Then he used sort of a feature selection. There are several ways to do that, and picked out the most important one. And I think he only used 3 or 4 here. And as you can see, the fit is not nearly as good, but it's still pretty good. Okay. Now we have just recently returned to this problem with a graduate student, whose name I will mention near the end, and interacting a little bit with my colleague here, Yanis Kavrakidis, who's really more of an expert in this than I am. Okay, so more complex models here. So there are a number of, so this just correlating the closure term is probably the sort of the simplest thing you can think of and the obvious thing to do, okay? There are still several challenges when you do that, some of which I will mention near the end. But the question is, can we do something sort of much more much different, particularly for very complex interface flows like what you see in atomization and so on, okay? So this is a thesis topic by Tom Chen, who is hopefully will be graduating next summer. But this one has sort of two main ideas, okay? First of all, instead of looking for the closure term and compare basically closure terms as you calculate them from the averaged fully resolved solution, can we dispense simply with the fully resolved solution and ask what modification do we have to make to the governing equation so that the coarse field evolves in the correct way, okay? So I'm not, so for example, a priori testing, where I test how my model for the subgrid terms compares to calculated values for the subgrid terms from the fully resolved solution and the averages of that, those become irrelevant. I just want the core solution to evolve in the correct way. I also, when I coarsen multiphase flow, I want to retain the interface, okay? So there are two ideas here. One is, can we come up with the models just from the coarse data, and can we coarsen complex interface flows in such a way that we retain the interface? Okay, so the first one, Tom did sort of a warm-up problem here. You can actually find it on the archive, but it is just two-dimensional turbulence. We average the flow, and so basically what we do here is that instead of computing the stresses from, as I say, the average of the product minus the product of the average, we didn't do that. We simply said, what does F have to be in order for you to evolve in the correct way? So that's the second step here. We just calculated F, and then we said, can we correlate that? And we didn't bother with sort of imposing various symmetries and so on. We did some symmetries, but not many. And then we said, okay, does this model allow us to evolve the flow such that the average flow evolves similarly to what the average flow it looks like from the fully resolved simulation? And the basic message here is, not surprisingly, this works, okay? For short time, we reproduce the flow. For the long time, we reproduce the average properties. Okay, so if you can find the closure terms from the evolution of the coarse field, what that does to us is that, or does for us, is that now I can do the coarsening in pretty much any way I want. I don't need to link it directly to the fully resolved flow. I just need the coarse flow to evolve in the correct way. So I can coarsen it in a highly nonlinear way. Indeed, I could coarsen it almost by just drawing it by hand. It would be rather tedious, but in principle, I could do it. So, so if we can coarsen the flow in other ways, we could, in particular, abandon sort of traditional filters and come up with filtering that is more conducive to retain the interface. So I'm going to show you one approach that we are working on. There are probably many other ways to do it. We haven't gotten too far into that actually using this for modeling, but we're making progress. So here is the idea. Here you have a jet, a highly idealized jet, and I want to separate the small and the large scale. And if you look at the right-hand side, the sort of the blue line here is now the large scale after I have filtered it. But when I filter it, I'm left with a whole bunch of small scales. So phase 1 that is mixed with phase 0, and phase 0 that's mixed with phase 1. Okay, and those are the small scales that I have to model. And then I want to be able to simulate the large scale evolution. Okay, so the question is, how do I do this coarsening where I retain the interface and separate out the small and the large scale? So we have we've actually used the fact that diffusion and filtering really are the same thing, at least in the simple case of a linear diffusion equation. We've used it before, actually for a very different idea, but what we're doing here is basically, instead of doing filtering, we're using the diffusion equation because we can now modify the diffusion equation, and in particular, we can make the diffusive operator nonlinear, because I can pick a diffusion coefficient that depends on the flow field. It won't give me a correspond exactly to a linear solution like we use when we do filtering, but it still is a coarsening operation. Okay, so for the interface itself, here is doing that. We just solve a diffusion equation for the marker function, and we track the interface as the flow is smooth. Okay, there are two types of smoothing that takes place, or reduction of the interface. One is when interfaces collapse, and also when they get straightened out. Now, I should say that this part of the operation we could do basically by diffusing the index function and then reconstructing the interface or the contour that corresponds to your interface. And this has actually been done by other people several years ago. Okay, but what we want to do is that we want to generate the mixture field and we want to smooth the flow field. Okay, so this gives me the smooth interface. Now, at the same time as we smooth the interface, we want to generate a mixture. And so what happens here is that as the interface is smooth, it leaves behind the other face on the other side, and that face is now mixed with the face on that side. Okay, so by doing this, we generate a smoother interface and we generate a mixture field on either side. So we do this by doing another diffusion operator simultaneously when we diffuse the index function, except that now we prevent diffusion across the interface. So we set diffusion coefficient equal to 0 at the interface, and we prevent the face. So the face doesn't cross the interface, but when the interface moves, the face left behind is mixed by the interface. Okay, so we often, this is just the same slide, we often work with the perturbation mixture fracture, because then it looks red in one phase and blue in the other phase. It actually has a negative value in the other phase, but it allows us to identify separately phase A mixed in phase B and phase B mixed in phase A. Okay, now this was just the distribution, the phase distribution, but we also want to do something with the flow. Okay, now we work with the momentum, we smooth the momentum, but the problem is when you smooth just the momentum in this way, you don't preserve incompressibility. So what we do is that as we smooth the momentum, we also solve a pseudo equation for the pressure, so the coarsened field retains incompressibility. Okay, so if you do that, here is a several frames for as we smooth it along with the interface. Obviously, for the largest degree of smoothing, we basically get a flat interface and a blob of one fluid moving up and the blob of another fluid moving down in the case of a Rayleigh-Taylor instability. When you smooth the velocity and then calculate the vorticity, you do find that the vorticity is highly concentrated on the interface because there is actually a slip on the interface. Okay, now I should note that I gave a seminar at UC Irvine, and it turns out that Perry Johnson, who by the way was actually a graduate student here at Hopkins but not working with me, actually has been developing similar ideas in the context of a single phase flow, where you also solve the pressure equation along with the smoothing. So just to acknowledge that, you know, this is not it's either not a totally wild idea, or if it is totally not a if it is a totally wild idea, I'm not the only one, you know, pursuing that. Okay, so once we have the coursed field, we want to, of course, evolve it. And so here is the model. We have the original interface, we filter the solution, and then we try to evolve the coursed field in a similar way so that it replicates basically the filtered solution. So the model, this is a very, very simple model, just a mixture model. So basically, there's an equation for the interface velocity, but the interface velocity doesn't always follow the fluid because sometimes it spills fluid across to generate small scales on the other side. We have a advection diffusion equation for the scalar, and there's a source term here given by this quantity that spills over. We have a density. We can solve a momentum equation here. Now, this is the momentum equation for the flow, not for the coarsening, where in this case we model this with some effective stresses. Okay, but of course you could use any kind of model for the evolution here. You could do point particles or two fluid models and so on. So this sort of looked okay. We are now trying to do a more sophisticated version of this. In this particular case, we simply guessed the parameters that we needed in order to replicate the flow. But we're now doing a more sophisticated problem. Tom Chen is working on this jet here, where he's doing, again, machine learning to relate the unresolved flow with the correlate the closure terms, basically the models, the multiphase models, with the evolution of the coarse term. And again, here's the model. Here's just an example of the coarsening. Basically, the time you diffuse determined how smooth the interface becomes, and depending on sort of how coarse you have to be, you can select that. And as you can see, here is the volume fraction on one side, the mixture field on the other, and we are basically working with different levels of smoothing here. And one is at an early time, and the other was at a later time. And this simple mixture two-phase model is listed down here, and this is the model parameters that we need to correlate. Basically, it is the slip velocity, it's the effective viscosity, and the diffusion coefficient. Okay, so hopefully we will have more specific results about this in not too long, and I can show that to you. But I wanted to leave a little bit of time to pontificate a little bit about the future. Okay, so let me just say, here's sort of the last slide on the coarse field. It's not the last slide of the talk. Basically, again, the idea here is that if you're happy with trying to work with just the coarse field to generate the closure form of the models, the reduced order or coarser models, you have much more freedom in how you coarsen it. And indeed, you can choose to coarsen in such a way that you retain features that you think are important, like a sharp interface, but which would be washed away if you did just standard smoothing. Now, even doing that, there are lots of challenges, and a lot of people are working on how can we do this coarsening in a way that preserves conservation, scaling, symmetries, et cetera, et cetera. Okay, so even in single phase flow, this is still an active research area. Okay, I promised to talk for only about 45 minutes. I have 2 or 3 minutes left. So I'm going to sort of talk a little bit first about sort of what I think are the immediate challenges. You know, it's sort of obvious to see where we are going in the short term. Let me stress again that we really have come a long way. And when you have been in the field for a long time, like you have seen actually things change significantly. The point I made in the beginning is basically that as we move to more complex problems, we are going to have a tougher time maintaining the rather high standards set by the definition of the direct numerical simulation. But on the other hand, we have a lot more experience with these kinds of simulations. So if we identify regions that may be under-resolved, you're in a much better position to judge whether it's a serious problem or not than we were 20 years ago. Again, the immediate challenge, or at least 2 immediate challenges, is to generate models for more complex problems and to examine multiphase and multiscale systems. So I put up 2 other graduate students here because they are working on problems related to that. Christina is working with me, and Jan is sort of revisiting this question of what are the important variables when we model coarse flow. The one that I showed you earlier that the graduate student who did this initial work sort of had started to do. And Dan is working on, again, multiscale models. We have done some multiscale models earlier where we use sort of pseudo-analytical models to capture the very smallest scales. And he is working on taking that to a new level. Okay. So, and as I say, I've listed a few others. Challenges such as, how to characterize coarse scales and things like that remains work in progress. Now, I told Bala that I would sort of, try to look at even further afield, and maybe I take the last minute here and to talk about what my dean likes to call adjacent possibilities. That is, It's not possible yet, but it may be possible, in sort of not too long. So it's not something that happens in the 22nd century, but maybe in the next decades or two. So first of all, let me say that, computational modeling is really changing in fundamental way. When I started doing this, it was pretty clear where we were going. We just needed better algorithms and bigger computers, and then it was sort of obvious what to do. Now it's not that obvious anymore. Even questions that were a hot topic 15, 20 years ago, such as verification and uncertainty quantifications, they're still important, but they're not really at the forefront. I think some of the topics that we are seeing and will be more important is that, my experimental colleagues are increasingly finding ways to do much more sophisticated measurements, including using some of the numerical tools that we have to actually fill in the blanks. So if you take that further, eventually what they will be able to do is just look at something and extract the information. If they can do that, if you can measure everything, you don't really need controlled experiments anymore. So I think in the future, we are going to see much more integration of data gathering, experiments, modeling, probably problem-specific modeling, and so on. Let me take one more minute just to sort of give you an example here. Suppose you want to model, say, how waves impact the construction of a new harbor. One way to do that would be simply to gather all the videos of waves that you can find on the internet, couple that with information, say, about topography and weather, and somehow integrate it into a model that conserves mass, momentum, and so on, and use that for your predictions. Okay, so maybe it is not possible now, maybe it will not be that possible immediately, but something along those lines probably is where we are going. Now, I have this warning at the very bottom here because, as we know, predictions of the future often capture sort of the general direction, but they're almost always incorrect in the specifics. And I'm pretty sure that this will be subject to that, just as any other prediction. With that, thank you so much. I hope I didn't go too far over, and I'm ready to take any question you may have.
Greater, thank you for a very delightful talk. And it's a perfect way to the last few slides captured for the younger audience the state of the field. Maybe not just for the younger field, for everybody. It left something for us to think about. I want to open the floor and please unmute yourself and ask questions. I do have a chat room, so I can read the chat questions, but first, I want to give people an opportunity to interact in live and ask questions. Go ahead. Anybody have a question? Okay, as people are thinking about it, I see a question on the chat, Greater. The question is, thank you for the illuminating and inspiring talk. I would like your thoughts on, there are two parts. One, DNS of coalescence and agglomeration phenomenon in GL and gas liquid and liquid liquid flows. And let me read the second question also, Greater. Using machine learning to address the interfacial phenomenon that control coalescence where the fluids are not pure but mixtures like oil and water.
Okay, this actually hits on something that I had thought a little bit about, and let me try to make it short. Okay, so we are certainly going to be using fully resolved simulations of well-defined problems to gain a better understanding of things like coalescence and so on. Even coupling it with multiscale models, even going all the way to molecular simulation. However, in real life, we may often find that things are just so complicated, it's almost impossible to make prediction without working with the real thing, okay? If I may jump to slightly different systems, suppose you want to model, the interactions of irregularly shaped solid particles. Okay, they come in a wide variety of types. You know, those of us who come from countries where people are interested in concrete know that different types of sand, you know, are good for concrete and other aren't. You know, people are stealing sand from rivers because Sahara sand is no good. So it's possible that when we develop these models, we are simply going to have to go to the experiment for that specific material. So maybe if you want to predict what happened to Sahara sand, you just have to do experiments on Sahara sand and use machine learning to correlate the properties. And they may not work with sand from your favorite beach, okay? So it's quite possible that that for these very complicated problems where you have, say, unknown surfactants or properties, maybe you're going to have to really just do experiments on that specific problem and then use machine learning to develop the correlations or the relationship that you want for your specific predictions, okay? You know, we all had this dream at one point that we would make experiment obsolete because we just could start at the very bottom and build that up. I think that dream has, as we have made progress, that dream has sort of receded a little bit. Sorry, long and perhaps not complete answer to the question. So.
No, that hits the point. Thank you, Greater. Any questions? I do have a question, but I want to give someone else an opportunity. Anybody wants to unmute and ask a question? Greater, I have a question. You really pioneered, you're the first one, if I may say it boldly, to use machine learning in multi-phase flow. That too, not too long ago, this is like 4 or 5 years ago. And then the field has exploded. I mean, we have done some work. But so one question I really want to ask you is, this problem of droplet breakup and interface, I mean, the people like Stefan and you guys have done marvelous job, but the direct simulation of 1 million droplets coming out of an interface, it's so daunting. So it's wonderful to see that there will be sort of an approximate approaches will be taken. So one thing I did not understand, let's say you do a coarse-grained interfacial simulation, but then the idea is that the machine learning will give you obviously, it cannot tell you precisely where the droplets are, but then it will give you the mixed region around that coarse grain interface. Is that the approach that you are pursuing?
Yeah. So basically, I think we are going to have to. So the dream was originally, you know, we would do this fully resolved simulations, and then you would coarsen that, and then somehow you could build it up. Okay. I think increasingly, again, maybe not to learn the fundamentals, but for practical predictions, you may simply have to measure some of the evolution of the coarse field. And then you ask, how do I modify the equations so that the coarse field at the scale that I'm interested in evolves in the correct way? Okay, and then hopefully I can apply that model to sort of a nearby certain situations. Okay, you know, in some sense, I hate to say that because it diminishes a little bit the role of the DNS, but which I still think is important. But I think this idea that you make predictions, you know, sort of from what you see, is going to play a bigger role as we move forward.
No, I agree, Greater, but in fact, it diminishes the role of DNS in the final prediction of practical system, but it increases the value of DNS in developing and testing these models that will. So in other words, people who are doing DNS will have a lot of work to do going forward, right?
Oh, absolutely, yes, yeah. Yeah, but the path forward, I think, is more complicated than what it looked sort of 10, 15 years ago. So.
Thank you. Any other questions from our distinguished audience?
Okay, there was a question that says, what with comparison with experiments, do they follow DNS? Okay. Oh, okay. So I think the integration of DNS with experiments is going to be, in many ways, quite different than what we thought originally. So if you know the equations and you can solve the equations accurately, you don't need experiments. Okay, and this was sort of a misunderstanding that was quite common in many years ago. People wanted to do experiment to validate my code, but if my code is correct and my equations are correct, I don't need experiments. But I still need experiments. I still needed experiments if I didn't understand the physics. Okay, that is, if I didn't know the constitutive equation for the surfactant, the ultimate test would be whether my predictions agreed with experiments. And so absolutely the experiment provides the source for the validation, not the verification, but the validation of the predictions. But I think as we move forward, as I've been trying to hint at, although it's probably not clear because it may not be totally clear to me, I think the interactions is going to be much more complicated than we saw. We're going to see experiments that use numerical simulations to sort of extract out the informations that are missing. We're going to see experiment provide input for systems that are simply too complicated to sort of build up the knowledge base right from the beginning. So.
Greater, go ahead. Somebody had something to say. Alfredo, go ahead.
No. There's just another question, but I think you defined DNS in the first or second slide. There's the question related to what is DNS. Yeah. So I think.
No, I was going to say, anybody can use DNS for anything. We're free to say whatever we want, but I wanted to sort of specify it and align it, almost exactly with what people who did DNS of turbulence meant. So in particular, it's not any fully resolved simulation. It really is. It is fully resolved simulation, but it has this additional sort of requirement, which, as I say, I think which align very much with what was originally the intent. So, okay.
I see one more question by Shankar. It says, I hope you are not arguing for the end of universal insight into multi-phase flows. I agree that for practical problems, the solution will be problem dependent, but the end of universality would be a grim prediction.
No. Okay. No, I most certainly did not mean to leave that impression. So let me just say the answer is rather simple. It's no.
Okay.
Shankar, I think we still have a job.
Thank you.
Wonderful. I want to report to the audience that we had at the peak about 150 people, about 120 joining by Zoom, and about 30 joining by 30 plus joining from YouTube. So this is really good, and I'm really glad that the speakers are powerful enough to attract such a large crowd. Alfredo, you want to finish off this session with your final comments, parting comments?
Well, my final thanks, Bala. My final comment would be just to be very thankful to Greta for such an inspiring and with the auspices that we will not be without job in the future. Actually, we will have more. That's our hope. And I also have to thank everybody in the audience. So thanks again, Greta, and thanks everybody. Look forward to meet you in 2 weeks from now.
Thank you so much. And I'm also looking for.
Thank you. Bye, Greta.